Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, today we're going to discuss about introduction to single sideband suppressed carrier systems. These are the outlines. We'll start up with the need of single sideband systems, followed by the brief introduction of single sideband systems. Then we're going to see about the frequency spectrum of SSBSC signals, which will be followed by the mathematical equation for SSB signals. Then we'll briefly describe about a special type of transform that is called Hilbert transform, and we're going to discuss some of its properties, which will be followed by the applications of single sideband signals. So this particular figure shows the spectrum analyzer view of AM signal. So if we briefly focus about this particular figure is we're going to have three components. Number one is your carrier signal, and these two are its sidebands. This is our upper sideband and this is our lower sideband. So we know that mainly message signal information contained in these sidebands. Upper sideband and lower sideband. Carrier does not carry any sort of information. So if it doesn't contain any information, so it would be better if we do not transfer this particular carrier signal so that we can save certain amount of power. Then again, in these two sidebands, in the lower sideband and upper sideband, we will be having information, but they are copied to each other. I mean, the information in the lower sideband and in the upper sideband both have same information. So if we could suppress one of the sideband and allow to pass only single sideband, then also the purpose of communication have been served, and by this manner we could further save certain power as well as the bandwidth. So in this particular single sideband systems, we are basically restricting our carrier signal as well as one of the sideband, either upper sideband or lower sideband, in order to save the power as well as the bandwidth. So we had already discussed that in order to design any communication system, the two important parameters that we need to focus is transmission power as well as the transmission bandwidth, and we actually wanted to reduce both the parameter. So in the AM double sideband full carrier systems or the traditional AM systems, both the transmission power as well as the transmission bandwidth both are very high. So in the AM double sideband suppressed carrier transmissions, power is less as we are suppressing the carrier signal in comparison to the double sideband full carrier system. But the transmission bandwidth is same since we are passing both the sidebands. So in amplitude modulated single sideband suppressed carrier systems or the single sideband systems, only one sideband will be transmitted. That is, we are only allowing one sideband to pass since both the sidebands contains the same information. Now the transmission power as well as the transmission bandwidth can be reduced. Reasons we have already discussed. So the transmission bandwidth will be reduced to half of that of the AM double sideband full carrier systems and the amplitude modulated double sideband suppressed carrier systems. So to accomplish these merits, the equipment design will be more complex. Obviously, we'll be having some more sophisticated filters to generate the SSB signals. So the generalized expression for the AM signal is being given as ST is equal to AC cos of 2 pi FCT plus AC MA cos of 2 pi FMT multiplied with cos of 2 pi FCT. We had already seen its derivation. So in this particular ST or modulated signal of AM signal, this particular part AC cos of 2 pi FCT represents our carrier signal, and AC MA cos of 2 pi FMT multiplied with cos of 2 pi FCT, this particular term shows the sidebands. So if we're going to exclude this carrier signal, we are left with this particular type of signal, which is called as your double sideband suppressed carrier systems. So now double sideband suppressed carrier signal would have been given as AC times of MA cos of 2 pi FMT multiplied with cos of 2 pi FCT. So again, we have just multiplied as well as divide by 2 in order to get this to cos A cos B formula. So we can write this particular expression as AC MA by 2 times of cos of 2 pi Fc plus FMT and cos of 2 pi Fc minus FMT. So this is our upper sideband and this is our lower sideband with the amplitude of AC times of MA by 2. This particular figure shows the spectrum of our message signal. We are assuming that we have a band limited signal whose maximum frequency is FM and whose spectrum is being given by this particular figure. So obviously after modulation we are going to have some frequency translated version of our actual message signal. So this particular signal will get translated along our carrier signal whose frequency is Fc. So this particular signal will get translated at our carrier frequency Fc. So now this particular portion shows our upper sideband as well as this particular portion shows our lower sideband, and these are the negative counterparts of our upper sideband as well as the lower sideband. So this is the spectrum of our double sideband suppressed carrier signal. So in single sideband suppressed carrier signals, since we are only allowing one sideband, so either we're going to have upper sideband or we're going to have lower sideband. So this particular figure shows our lower sideband only, whose negative frequency version will be given by this particular figure. This is your single sideband suppressed carrier signal with lower sideband, and last figure shows the single sideband suppressed carrier signal with the upper sideband. This shows our upper sideband and this particular figure shows the negative frequency part of our upper sideband signal. So this particular figure shows the frequency spectrum of single tone signal. It means in our message signal we will be having only single frequency component, which has been given as your omega m. Here we are using the term omega m as the angular frequency. We could also write it omega m is equal to 2 pi of fm, where fm is the maximum frequency component. So since it is having only single frequency component, so it is being shown by this particular arrow, whose negative frequency or negative frequency part is being given by this particular arrow. So after modulation, these frequency will get translated to the higher frequency band, that is your omega c plus omega m. This is our upper sideband, and omega c minus omega m, which is our lower sideband. And these are the negative counterparts of our upper sideband as well as the lower sideband. Since in single sideband suppressed carrier systems we are only allowing one sideband and we are suppressing the other one, so this particular figure shows the lower sideband signal and this particular arrow shows the negative frequency component of our lower sideband, whereas this particular figure shows the upper sideband component of our modulated signal and this particular arrow shows the negative frequency of my upper sideband signal. So now we're going to discuss about the mathematical equation for SSPSC signal. So let us say the single tone modulating signal or message signal is being given as xt is equal to cos of omega mt. Here we are assuming its magnitude is unity and it is having only a single frequency component, which has been denoted by this omega mt. So as the basic definition of SSB signal says that we have only one sideband present, hence the single sideband suppressed carrier wave with lower sideband would have been expressed as cos of omega c minus omega mt. So now after expanding this particular expression, we will be having we have applied cos of A minus B's formula, which has been written as cos of omega ct cos of omega mt plus sine of omega ct into sine of omega mt. In the same manner, we can write the expression of single sideband suppressed carrier wave with upper sideband as cos of omega c plus omega mt is equal to cos of omega ct into cos of omega mt minus sine of omega ct into sine of omega mt. So now we can combine both these equation up, so we can have the generalized expression for SSB signal as cos of omega ct cos of omega mt plus minus sine of omega ct into sine of omega mt. So this equation combinedly, obviously we're going to take one sine at a time, either cos of omega ct cos omega mt plus sine of omega ct sine of omega mt, or cos of omega ct cos of omega mt minus sine of omega ct sine of omega mt, represent the actual SSPSC waveform. So in this particular expression, we can also write sine term with this expression. Sine of omega ct would have been represented as cos of omega ct minus pi by 2. Similarly, sine of omega mt would have been written as cos of omega mt minus pi by 2. So hence we can conclude that the cosinusoidal term can be obtained from the sinusoidal term by just giving 90-degree phase shift. So now the question arises, how we will going to implement such a system which could provide the minus pi by 2 phase shift to each and every frequency component of our message signal. So the solution is Hilbert transform. So Hilbert transform is an operator which actually provides minus 90-degree phase shift to each and every frequency component present in the message signal. So in general, if we talk about the transforms, we are actually being talking about, we are converting our signal from one domain to another domain. The most commonly used transformations are Fourier transforms, frequency transforms, Laplace transforms. These are the transforms that we have already studied, and they actually converts our time domain signal to the frequency domain signal. But the Hilbert transform transforms a time domain signal to the same time domain signal. It has been defined as xh of t is equal to 1 of pi xt convolved with 1 of t, where xt is some time domain signal and xh of t represents its Hilbert transform. So Hilbert transform is being defined as the convolution of the signal with 1 upon t multiplied with 1 by pi. So it could have been written as 1 over pi, integration starts from minus infinity to infinity, x of tau t minus tau d tau. And in the similar manner, the inverse Hilbert transform would have been defined as x of t is equal to 1 upon pi, integration starts from minus infinity to infinity, xh of tau t minus tau d tau. These are some of the properties of Hilbert transform which are really important. So the signal xt and its Hilbert transform xh of t both have the same energy density spectrum. Since we have studied that Hilbert transform is doing nothing but it is actually being producing minus pi by 2 or minus 90-degree phase shift to the original signal, and we know that energy and power does not depend upon the phase angle. So that is why we can conclusively say that both xt and x of h of t or the Hilbert transform of x of t has the same energy density spectrum. Since energy density spectrum is the distribution of energy over the frequency domain, so we could say that the energy of x of t and xh of t both will going to have the same magnitude, and since they have the same bandwidth, that is why we could say that both of them will going to have same energy density spectrum. Second important property of Hilbert transform states that the signal xt and its Hilbert transform xh of t both have the same autocorrelation function. This is one of the most important property, and it would have been really important for different competitive examinations too. Third property is the signal xt and its Hilbert transform xh of t both are mutual orthogonal to each other, or mathematically we could say that integration starts from minus infinity to infinity, x of t xh of t dt will be equal to 0. Proof is quite simpler. Let us assume that signal x of t is equal to cos t and its Hilbert transform turns out to be cos of pi by 2 minus t, that turns out to be sin t. So simply after multiplying 2 sin t cos t upon 2, which is equivalent to sin 2t upon 2, integration starts from minus infinity to infinity. So since sin 2t is an odd function, so integrating within the limits of minus infinity to infinity, we are left with 0. So next property is, if the xh of t is the Hilbert transform of xt, then the Hilbert transform of xh of t is minus xt. This proof is also quite intuitive and quite easier. We could easily say that, let us say if we are taking any signal x of t and if we are taking its Hilbert transform, it means we'll be having minus 90-degree phase shift from the original signal xt. And if we're going to again take the Hilbert transform of x of t, then obviously we're going to have total 180-degree phase shift. So we could simply say that the Hilbert transform of x of t turns out to be minus times of x of t. So the applications of SSPSC signal. The SSP transmissions is used in the applications where the power saving and the low bandwidth requirement are important. So the major application areas are land and air mobile communication, telemetry, long distance telemeasurement, military communications, navigations and amateur radio. These are the certain application areas. Many of these applications are point-to-point communication applications. These are the references. Thank you very much.